Hi, welcome to the first lecture on energy in the Energy and Sustainability course. Today we're going to talk about the concepts of energy and heat. Um, these concepts of energy and heat are somewhat mysterious. They play a very fundamental role in the development of order and structure in the universe. And there's a lot we still really don't know about energy and heat, as we will discuss as we go further in the course. So just know that there's a lot of practical uses for energy, renewable energy, but that there's fundamental roles that they play in the universe that are somewhat mysterious. So we're going to go, first thing we're going to do is take a walk into the physics, the physics lab, and at MUM, we might call it the metaphysics lab, and learn a little bit more about these fundamental physical qualities of energy and heat. First, I want to talk a little bit about work. Work is something that makes a change in the universe. Now, energy is the ability to do work. Now, when I talk about a change in the universe, what do I mean? I mean something like a change in elevation in a gravitational field, a change in temperature, a change in pressure, a change in in the chemical concentration of something. These are all changes in the universe. So anytime we make a change in the universe, it takes work, and energy is the ability to do that work. The basic unit of measure of energy is something called joules. Now, power is different than energy from a physical perspective. We often talk about, well, I have a lot of energy today, or I'm feeling very powerful, and we don't really, in an informal sense, we don't really make a distinction too much between the two. But there's a really strong distinction that I'm going to make over and over again in this course. And one thing I want you to get when you get out of this course is that you understand the difference between energy and power. Now, energy is a total quantity. It's a total quantity of energy that it takes to make some kind of change. So if I lift something up 50 feet in the air, it's going to take a certain amount of energy to make that transformation, to make that change in the universe. I could do it very slowly. I could take a week to pick that heavy weight 50 feet up in the air, or I could do it very quickly, and I could do it in 3 minutes. The energy would be the same, but the rate at which I was using up that energy, or performing that task, would be different. Now, power is the rate at which work is done. It's the rate at which energy is produced or consumed. And as a rate, it's in joules per second. So energy is in joules, power is in joules per second. We'll talk more about other things that where one thing is a rate and one thing is a total quantities, to help you understand that a little bit better. Now, when we talk about different forms of energy, like heat energy or electrical energy, it's customary to use different kinds of terms to measure that energy, measure that power. So, for example, with heat, we often use something called the BTU, or British Thermal Unit, and it's defined as the energy it takes to raise 1 pound of water up 1 degree Fahrenheit. So when we're talking about heat, we often use BTUs. Calories are just the metric equivalent of BTUs. When we talk about electrical energy, we talk about watt hours, which are 3,600 joules, or kilowatt hours, because watt hours are pretty small. And we'll talk again a little bit more about those later. I just want to introduce these terms to you now. And then when we talk about power, and again, remember, power is the rate at which we're producing or consuming energy. We talk about joules per second. Now, joule per second is hard to say, so we use the term watts. Watt is defined as a joule per second, and kilowatt is just 1,000. The term kilo in front of something usually means 1,000. Like kilogram is 1,000 grams, so kilowatt is 1,000 watts. And then BTUs per hour is a rate at which thermal energy might be flowing in a system. And horsepower, we use that when we're talking about things like motors and engines and things like that, like your car engine or an electric motor. We talk about it in terms of horsepower, and that's just 746 watts. It's producing or consuming power at a rate of 746 watts. So let's talk a little bit more about a couple of these that are used commonly. The British Thermal Unit, again, commonly used for measuring heat energy, is actually a pretty small quantity. A BTU is roughly the amount of energy that's released when you strike a match, and it takes tens of millions, sometimes hundreds of millions of them to heat your house through a winter, through a cold winter. So it's a small quantity, and you typically talk in terms of tens of thousands, hundreds of thousands, millions of BTUs. Now, for electrical energy, we talk in term the unit of energy that's used is the watt hour. Now, watt hours, again, typically used to measure electrical energy, and it's a pretty small unit. It takes 50 of them to make a slice of toast. So again, because they're so small, we talk about them in terms of kilowatt hours or thousands of watt hours. And that's what you buy from the power company. You buy a kilowatt hour. In the United States, it costs typically between 10 and 40 cents. A place like Hawaii, 40 cents. A place like the Pacific Northwest, where they have a lot of inexpensive hydroelectric power, 8 or 10 cents a kilowatt hour. And a typical utility connected family uses about 1,000 kilowatt hours per month. So a lot of people pay somewhere between 80 and $300 or $400 a month for electricity. Now one thing about these units is that you can convert them from one form to another, from one to another. So there's a direct conversion. And we'll talk about that. It's again part of this kind of mysterious quality of energy, and that energy can be, is not used up. It's converted from one form to another. 1 watt hour equals 3.41 BTUs, and a kilowatt hour is, again, just 1,000 of those, 3,410 BTUs. And I remember this because it's very close to the number pi. The number pi is 3.1417, and a BTU is a watt hour is 3.41 BTUs, or 3,410 BTUs. So it's very close. If you just turn those two numbers around, the 4 and the 1, if you remember pi, the number pi, then you can remember this number very easily. So let me just summarize what we've been talking about so far. First off, energy is the ability to do work, and it's absorbed or released when some kind of change happens in the universe. Examples of changes include a change in pressure, a change in temperature, a change in voltage, a change in chemical concentration, and a change in gravitational field, in elevation in a gravitational field. And power is the rate at which that energy is produced or consumed. Now we take that back and think about Maharishi Vedic science and our experience in meditation. In order to do, one must think, and in order to think, one must be. Therefore, the source of action and change is ultimately being. Like in the universe, the source of action and change ultimately has to do with energy in some way or another. Now let's talk about power units. We talked about energy units, which were watt hours. And the power units, the rate at which energy is produced and consumed, is the joule per second. And that's because that's difficult to say, joules per second, then that's been defined as a watt. Now again, a watt, just like a watt hour is a small number, a watt is a small number. It takes 1,000 watts to run your toaster. So when you push the lever down on your toaster and start that going, it's consuming energy at a rate of about 1,000 watts. So or a kilowatt. 1 kilowatt is 1,000 watts. And again, that would cost, if you let your toaster run for an hour, it would cost you somewhere between 8 and 40 cents, depending on where you lived in the U.S. It's about 15 cents here in Iowa. So again, 1 kilowatt equals 1,000 watts, and again, a kilowatt is a rate. It's how fast something is producing or consuming energy. In this case, electrical energy. And it's also equal to 1,000 joules per second, because 1 watt is a joule per second, so 1,000 of them is just 1,000 joules per second. Again, this is, it's a lot to hear these words, but actually when you work with them, it's much simpler than what it sounds as I'm saying them out loud. Now, when you look at an appliance, you want to know how much energy it's going to use, or what rate it's going to use energy at. Then you look on the label for the appliance, and you will often see the wattage of that appliance listed. Now, remember, that's watts is not energy; it's power. It's the rate at which that device is consuming energy, and the reason why you don't see the energy listed is because it would depend on how long the device was on. So the energy is the total amount that's used up over the whole period of time the thing's on, and then the power is the rate at which it's doing that. So, for example, this television, TX, color television receiver, it's probably a label from a very old style television. It uses 130 watts when it's on. So, and then if you look at this food steamer, for example, it uses 900 watts when it's on. So let's take a quick look at that. So here's the 900 watts for the food steamer and the 130 watts for the television. And this is typical of what you will see if you look at the energy consumption. I mean the power that a electronic device will consume. It's typically much smaller than the power that some kind of device that uses heat, like a toaster or a heater or a food steamer or something like that, will use. So again, to summarize, power is a measure of energy flow, the rate at which energy is produced or consumed. And consciousness flows effortlessly from being to form the universe in an analog way to power flowing to produce some kind of change in the universe. There are many different forms of energy, but they all fall down into two different categories. So the forms of energy are things like gravity, chemical energy, energy due to your place in a magnetic field, nuclear energy, rotational energy, sound energy, heat energy, electricity. But they all come down to two different forms of energy. One is kinetic energy, which is related to movement, and it's something that's happening right at the moment, some kind of movement that's happening. So, flowing water, flowing wind, sunlight, that flow of light energy. Now, potential energy is related to the position or state of the system. So, for example, a ball that's at the top of the hill that could roll down the hill, that ball isn't rolling down the hill, but has the potential to do that. So it has inherent in it potential energy because of its position in the gravitational field. So again, two different main forms of energy, hundreds of different types of energy, but two different main forms of energy, kinetic and potential energy. Now, being is pure potentiality, but in contrast, the manifest universe is eternally in motion. So being, you can think of like potential energy. It's the potential of the universe to manifest. And in contrast, the actual manifestation of the universe is like kinetic energy. So another mysterious, we're starting to get to the mysterious part of energy. It's neither created nor destroyed. You don't ever make energy and you don't ever destroy energy, but you can create it and you can change it from one form to another. So energy is neither created nor destroyed. It eternally changes from one form to another. Like that saying from the Vedas, curving back on myself, I create again and again. The unchanging unified field is neither created nor destroyed, but gives rise to the cycles of creation, maintenance, and destruction at the surface of life. So I'm going to show you an example of this from a famous professor at MIT, Professor Walter Lewin, and he is known for doing very dramatic demonstrations of physical principles. So here he's talking about this strange kind of property of energy, and it's neither created nor destroyed. So let's just listen to Professor Lewin for a minute.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, they're called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
So I encourage you to go online and look at some of Professor Lewin's other examples of illustrating principles of physics. So what Professor Lewin is showing here is that there is no wasted energy. Energy doesn't disappear. It was converted from the height. He raised that wrecking ball to flowing kinetic energy, converted back into height at the end of the other swing of it, but there wasn't any energy that was, it was changed from one form to another, but it wasn't created or destroyed. Now, energy can lose its usefulness. So let me give you an example. If I put a gallon of gasoline in a car and I drive that car down the street, that gasoline is going to be converted into a variety of different other kinds of energy. The energy of forward motion of that car, the friction of the car against the air, the atmosphere, the friction of the tires against the road, the heat coming off the radiator and the exhaust. About 80% of the energy in that gasoline is going to come out as heat from the radiator and exhaust, and you can think of that in some ways as wasted because it's not providing you with forward motion of the car, but it didn't disappear. It just isn't doing something useful for us. So when I get done with that gallon of gasoline, it's been converted into a bunch of different things. The same amount of energy is there. The same amount of energy that was in that gasoline, about 140,000 BTUs per gallon, is in all those, the heat in the engine and the friction in the tires and all those other things. But we can't take that energy now that's been dispersed through heat and through friction and all that and put it back in the car and drive the car. That's what I'm talking about by usefulness. So that in some ways that gasoline was a highly orderly, useful form of energy, and I've converted it into forms that I can no longer use in the same way. So this is a very, again, very mysterious and fundamental property of energy that affects everything you do every day. And we'll talk more about that tomorrow when we talk about the laws of thermodynamics. So again, we can easily convert energy from one form to another. So, for example, we look down this list, we can convert from mechanical energy to another form of mechanical energy using gears and pistons. We can convert energy of a rotation into energy of something moving up and down through a piston. We can change mechanical energy to electrical energy through an electric generator. We can move magnets next to wires and they take the rotational energy of those magnets moving near the wires and create electricity. We can take mechanical energy and turn it into heat. I can do it just by taking my hands and rubbing them together, and you can do this just as we're talking, and you'll see that you've converted mechanical energy of the movement of your hands into heat through friction. And again, we could go down and look at all these various ways in which energy is converted from one form to another, and this is really what we need to do in terms of creating using renewable energy. We've got to think of all the ways in which we want to get services from energy, and how can we take the basic forms of renewable energy, solar energy, wind energy, the energy in moving air, water energy, the energy in flowing water. It could be waves, it could be water in a stream, water falling over a dam, the heat energy of the earth, the geothermal energy of the earth. All these are kind of our basic forms of energy, and how can we take those and turn them into useful services. So again, I'll just mention one or two more. We can take heat energy and turn it directly into electricity with an interesting device called a thermocouple, and I'll show you that later in the course. It takes heat and changes it directly into electricity with no moving parts. We can take chemical energy and turn it into electrical energy with a battery. So again, many different forms of energy, many different ways of converting them from one form to another. Now again, I want to go back to this idea about power being a rate at which energy is produced and consumed, and energy being a total quantity. And another place in which you see these two different ways of thinking about something is in the speedometer of your car and the odometer of your car. Now the speedometer of your car tells you how fast you're going at any instant, 60 miles an hour, 70 miles an hour, and it changes all the time depending on how fast you're going. But your odometer clicks off how many total miles you've gone. So for example, if you're going 50 miles per hour for 4 hours, then you're going to have gone 200 miles and your odometer will have clicked off 200. And so again, that energy is a total quantity like what you'd read on your odometer, and the power is the rate at which you're producing or consuming that energy, the rate at which you're clicking off those miles. That's again just to illustrate the difference between power and energy. So we're going to do some simple energy transformation calculations in the classroom tomorrow. I'm going to save these for that. I'll do a few examples in this lecture later, but I'm going to skip out of this presentation for a minute and go to Google and show you something interesting. Now Google has built into it a calculator, a transformation calculator. And so if I put in, for example, 100 kilowatt hours in BTU, Google should come back and tell me. You see there's a special window at the top of Google, and it says 100 kilowatt hours equals 341,000 BTUs total. So you can easily go in here and put in, if you're working on a problem, you can use Google to just translate the units for you. If I wanted to know just 1 kilowatt hour, just what the conversion factor is, then I would just type that in and it'll tell me it's 3,412 BTUs. Let's get back to our presentation. So now I'm going to talk a little bit about heat energy. And heat energy is a special form of energy that has, again, some mysterious properties. And it's very useful in sustainable systems design. We need to heat and cool our houses. We need to affect the flow of energy through our houses. We need to heat our water for taking showers and baths. There's a lot of processes, industrial processes that require heat. So heat's very useful form of energy, and heat, again, is a very kind of mysterious form of energy. So let's talk about some of the things we know about heat. Now, so heat is energy that comes from molecular motion. So heat is related to sort of what's the energy of those molecules within a substance. And when we heat it up, they're kind of more active, and when we cool it down, they're less active. Now, another unusual thing about heat is a form of energy that flows from warm to cold objects. So if something was warm and it becomes cold, we know that heat flowed out of it. If something is cold and it becomes warm, we know that heat flowed into that object. Now, heat, not only is heat the form of energy that flows from warm to cold, heat spontaneously flows only from hot to cold. So, for example, give you an example. I take a cup of hot coffee, I put it on a table. What's going to happen? It's going to get cold. Take a cup of cold coffee, put it on the table. Is it ever going to get hot? No. So this is, again, a kind of an amazing property of heat energy is it flows spontaneously from hot to cold. Now, we can move things from heat from cold objects to hot objects, but it takes energy to do that. For example, a refrigerator. The box inside a refrigerator is colder than the temperature in your room, and you take energy and you're able to move heat from that inside your refrigerator out to the room, even though the room's warmer. But it takes energy to do that. It doesn't do it on its own. Now, another unusual thing about heat energy is other forms of energy can be converted to heat at 100% efficiency, which isn't true. Like, you can convert of other energy conversions. Typically, if you convert one form of mechanical energy to another form of mechanical energy, some amount of energy is always lost, and that lost energy always shows up as heat. So, but you can convert, for example, electrical energy. 100% of the electrical energy will be turned into heat. Now, you won't be able to do the kind of useful things you did with electricity with that heat energy once you do that, because, again, it's a different quality, and we'll talk a little bit more about that tomorrow when we talk about entropy and the second law of thermodynamics. Now, let's talk about temperature. Now, a lot of people equate temperature and heat energy and temperature as the same thing, but they're really quite different. Temperature is what increases when energy flows into something and decreases when energy flows out of something. So let's say that you have a cup of water that's at 100 degrees, and you come back later and you see that it's at 120. You know that energy must have flowed into that cup and increase the temperature. And same thing if you come back, you have a cup of water at 100 degrees and you come back, it's 50, you know that energy flowed out of that cup. So temperature increases when energy flows into something and decreases when energy flows out. Temperature is not heat. Now, let me give you an example of that. Which involves more heat flow? Heating 10 pounds of water from 55 degrees to the boiling point, which is 212. Now, that's quite hot. You burn yourself very easily at 212 degrees Fahrenheit. It wouldn't take very long to burn yourself with that kind of temperature. So it seemed like, hey, there's a lot of heat there, heating 10 pounds of water from 55 degrees to the boiling point. Or is there more energy involved in lowering a 70-degree swimming pool to 69 degrees? Now, you wouldn't even notice that. You couldn't even feel the difference between the temperature of 70 in the pool and 69 in the pool. So it seems like, there's not very much temperature involved. There's not very much energy. But let's do the calculations on that. Let's go through that calculation. So if we heat 10 pounds of water from 55 degrees Fahrenheit to the boiling point, 212, how many BTUs are involved? Well, let's first take a look at the definition of a BTU. BTU means 1 pound of water up 1 degree Fahrenheit. So I want to know the total amount of BTUs that's involved in some kind of energy transformation. I need to know the pounds of water, and I need to know the degrees Fahrenheit. So in this case, I'm given that there are 10 pounds, and I can calculate the temperature difference because I know the end point, 212. I know the starting point of 55, so I just subtract the two, and I get 10 pounds times 157 degree temperature difference. I get 1,570 BTUs. Now, we'll go over these kinds of calculations more in class tomorrow, but I hope that makes sense to you. Now, let's take a look at how much energy is involved in cooling a swimming pool from 70 to 69 degrees. Now let's just make an assumption that there are 100,000 gallons of water in the swimming pool. How many BTUs are involved in moving that from 70 to 69? Again, we'll use a similar thought process to what we used with the other example. And again, look at the definition of a BTU as moving 1 pound of water up 1 degree Fahrenheit. So we need to know how many pounds of water are involved and how many degrees Fahrenheit. Now in this case, we're not given the pounds of water, we're given the gallons. But I could go to my Google conversion and I could say, 1 gallon of water equals how many pounds, and it will tell me, and it's about 8 pounds per gallon. Now, and then the other thing I need to know is how many degrees Fahrenheit. Well, it's just a difference, 70 minus 69, it's just 1 degree. So I have the pounds, which is 800,000 pounds, 100,000 gallons of water times 8 pounds per gallon. I have the temperature, which is just 70 minus 69, 1 degree temperature difference. So I get a total of 800,000 BTUs. So look at, there's 800,000 BTUs involved in cooling that swimming pool. And that's energy that's going to be liberated. It'll actually make the room a little bit warmer if you were to do that. And but when I change water from 55 degrees to 212, it's only 1,570 BTUs. But when I change that 1 degree temperature of the swimming pool, it's 800,000 BTUs. So can you begin to see why there's such a difference between temperature and heat? Temperature, again, is this kind of measurement of when energy flows into something, it goes up, and it's a measurement of kind of how relatively active that substance is. But the heat is actually a total quantity of energy. So let's talk a little bit about heat transfer. There are 3 modes of heat transfer. Conduction, which is heat flow by direct contact between objects. So 2 objects that are right side by side, touching each other, heat is going to flow by conduction. You can think of it this way. The hotter object, the molecules are moving a little faster. The colder object, they're moving a little slower. When they touch each other, some of the energy of motion of the hot object in those molecules is going to rub off on the slower moving molecules in the other object, and the heat is going to flow from the hot one to the cold one. Now the second method of heat transfer is through convection, and this is heat flow by fluid motion. So what happens here is, for example, in this pot, you've got heat that is being applied to the pot at the bottom of the pot. So the bottom of the pot is heating up, and then when you heat a fluid like water or air, it becomes less dense and it rises. It rises up to the top. So in this case, the water is rising to the surface of the pan, and then it's giving off its heat at the surface of the pan, and it will become heavier and drop down, and then it will become hot at the bottom and get light and rise, and you'll get these loops forming, and that's called convection. That's heat flow by convection. It happens, for example, in a room with a heater near the floor, and it's heating up the air in the room. The air rises to the ceiling of the room. The air gives off some of its heat to the ceiling and cools off, falls back to the ground near the heater, picks up some heat, becomes less dense, rises again, and you start a convection loop. So conduction, convection, and the third way is radiation. Now radiation, again, is a very interesting kind of form of energy because it flows even if there's no contact, or even if there's no air or water or anything in between the 2 objects, even if there's a vacuum between the 2 objects, like the sun and the earth. And it flows from hot objects to cold objects, and it's actually a form of electromagnetic radiation, like a form of radio waves or light waves. And it flows, every object, like my body, which is at 98.6 in this room where I'm doing this lecture, the walls that surround me are cooler, and my body is radiating to all these cool walls in this room, and they're being heated to a small extent by the radiation from my body, just because it's warmer than the walls are, and it would be heated even if there wasn't any air in the room. Again, now, how can we slow this energy flow? Now, if we want to slow conduction, then we can put insulation, and that's what we do in buildings. We put insulation in buildings, or a thermos bottle, we put insulation, and we slow that flow of energy by conduction. By convection, what we do is we stop those convective loops. So what you can do there is that you have to find some way of stopping that loop of warm fluid rising, cooling off, and then going back and picking up heat again. And then for radiation, it's stopped by shiny surfaces. So if I put a piece of tinfoil between my face and the sun, I'm feeling the warmth of the face of the sun on my face, put a piece of tinfoil up there, that tinfoil is going to block the energy of the sun and I won't feel it. So those are 3 ways in which we can slow the flow of energy, different kinds of energy flow. If we think about heat loss through walls, let's say this is an example of a house and the inside temperature is 70 and the outside temperature is 20. Which way is the heat going to flow? Remember, heat always flows from warm to cold. So in this case, the heat is going to flow from, let me see if I can get this pen to work. Pointer option. So in this case, the heat is going to flow from inside to outside. Okay? And then it's going to be slowed by the insulation that's in that wall. And insulation is the term used for the measurement for insulation is R value. And the higher the R value, the better the insulation. So the heat loss, the formula for heat loss is the area of this wall times the temperature difference between the inside and the outside divided by the R value. And so here you see if the R value is larger, then this heat loss is going to be smaller. And so larger R values give you less heat loss. Now the inside temperature minus the outside temperature, that's something that's used a lot in heat loss calculations, and it has a name called delta T, or change in temperature. The change in temperature between the inside and the outside is 50 degrees, the delta T here. And the higher the delta T, if I made the inside temperature 100 degrees, then there'd be more energy flowing to the outside. If I double the temperature difference, I'll double the amount of energy that flows from inside to outside. If I lower the outside temperature, keep the inside temperature the same, I'll also have more heat loss. So the bigger the temperature difference drives the heat loss through that wall, and the R value slows it. Talk just a minute about the human comfort and the sensation of heat, temperature, and humidity. So humans don't just feel the temperature. The comfort level of a human is not just directly related to the temperature. It's a complex equation that's related to the temperature, humidity, and heat flow. Let me give you an example of an experiment that the Navy did. They took a naked person, put them in a room that they could control the surfaces of that room and can control the air temperature. So they took that naked person and made the surfaces of the room 85 degrees, but they made the air temperature 40 degrees. And the person was perfectly comfortable because their body was radiating energy to warm surfaces in that room. So the person could be very comfortable even at a low air temperature. Now, if you take the reverse, they took and made the surface temperatures of that room like 40 degrees, and they made the air temperature 75, and the person was freezing because even though the air temperature was warm, their body was radiating to all these cold surfaces. So in a building, the radiant temperature of all the surfaces that surround you is very important to your human comfort. You notice how warm and cozy you feel next to a wood stove or laying on a warm rock where that heat is radiating directly to you. And if the air is more humid, you'll feel less comfortable you'll feel comfortable. You'll have to have a lower temperature to feel comfortable with humid air. If the air temperature is warm and you're comfortable, and all of a sudden becomes more humid, you'll be less comfortable. So humidity also affects your ability to be comfortable in any given situation. So again, the human comfort is a complex combination of heat, temperature, and humidity. One other factor about heat, and this is related to heat storage, it's called specific heat. So how do we, if we have excess solar energy coming into a building during the day, how can we store it, take advantage of it, and actually have that solar energy, extra solar energy from the day available to us at night? Well, we can use materials that store energy. So let's talk about that a little bit. So the energy storage capability of any material is called specific heat. And again, it's the energy required to raise 1 pound of that material 1 degree Fahrenheit. Now we know from a definition of BTU that a BTU, 1 pound of water raised up 1 degree Fahrenheit makes a BTU. So that's the specific heat of water. But for stone and concrete, it's 2/3 of a BTU per pound per degree Fahrenheit. So if you put in just 2/3 of a BTU, you'll raise that material up 1 degree Fahrenheit. And if you cool it 1 degree Fahrenheit, you'll only get back 2/3 of a BTU. So you can see different materials, but again, water has this a lot of mysterious qualities that make it uniquely suited to help support life on Earth. And one of them is the fact that it can store a lot of thermal energy. And so let's take a look at how much energy we might be able to store in the earth blocks of the Sustainable Living Center. The walls of the Sustainable Living Center, the inside walls of the Sustainable Living Center are made of earth block, and there's about 600 tons of them. So let's calculate how much energy we can store in that SL Center earth block for each degree of temperature that we raise or lower it. So again, looking at the specific heat of earth block, it's 0.25 BTUs per pound per degree Fahrenheit. So we have to know how many pounds of earth block we have. We know it's 600 tons, 2,000 pounds per ton right here. That gives us 1,200,000 pounds of earth block. Now what's this heat storage capacity of that? Well, for each pound I get 0.25 BTUs for each degree Fahrenheit. I raise it up. So in this case then I get 300,000 BTUs per degree Fahrenheit for the whole building. And to give you an example of that, a gallon of gas is about 140,000 BTUs. Let's say 100,000 BTUs for this example. So every time I change the temperature of that wall, it would take the equivalent of 3 gallons of gasoline to heat it 1 degree. And if I cooled it 1 degree, I'd get the energy equivalent of 3 gallons of gasoline back. Now, in the worst case, the heat loss for our building in the 10 degrees below zero in the wintertime, 70 degrees inside the building, is about 80,000 BTUs per hour. Now, if we were to raise the temperature of the, when we have extra solar energy during the day, raise the whole temperature of the building up 10 degrees, maybe from 70 to 80, 10 times 300,000 would store 3 million BTUs of energy in the walls of that building, which as we cool the building off at night from 80 back to 70, we could get that 3 million BTUs back. And so this is a way in which we could use the walls of the Sustainable Living Center to store surplus solar energy. We don't do that now. We could operate the building differently. And somebody remember to ask me why it isn't done in the Sustainable Living Center now. And we'll talk about that tomorrow during class. We also have in the Sustainable Living Center a 5,000 gallon water storage tank. So we have 2 kinds of solar panels on the roof of the Sustainable Living Center. One kind that makes electricity and one kind that makes hot water. So the kind of solar panel that makes hot water takes the heat of the sun. We have the capability of taking, on a sunny day, taking several days of solar energy and storing it in that 5,000 gallon water tank. So let's go ahead and calculate for each degree we change the temperature of that tank, how many BTUs we can store. So again, we're back to this equation, 1 BTU, the specific heat of water is 1 BTU per pound per degree Fahrenheit. So in this case, we know how many gallons, we have to figure out how many pounds. So 5,000 gallons times 8 pounds per gallon is about 40,000 pounds of water. The heat storage capacity is 1 BTU per pound. So for every degree Fahrenheit that we change that water temperature, it's going to involve 40,000 BTUs. Again, a gallon of gas, about 100,000. So 2.5 degrees change in that water tank equals a gallon of gasoline. So we might start that water tank at 70 degrees and raise the temperature up to 170 degrees, which would be 100 times 40,000, be about 4 million BTUs of heat energy that could be stored in that water tank. And again, that could help heat the building for several days with no sun. There's also a heat flow time lag. So when the sun hits, let's say that the sun is going to hit this wall, and this wall is, let's say, a stone wall, a masonry wall, concrete wall. It will start to flow through this wall, but it will flow through it at a rate of 1 inch per hour. So if this, this is used, for example, in the desert, where it's really hot during the daytime but cold at night. So you can take that heat at noontime, you might be 100 degrees, that's the solar energy that's hitting the side of the building, and you can slow it so that it won't enter the building until maybe 7 or 8 hours later, 7, 8 o'clock at night, when maybe the temperatures drop to 40 degrees in the desert, and you could really use that heat inside the building. A building design feature called a trom wall is designed to do just that, and we'll talk about that in just a second here. Let's talk about that right now. So here's a trom wall. So a trom wall, you can see that in the wintertime the sun shines against this glass, which is in front of a concrete or stone wall. So the sun shines through that glass, hits that concrete or stone wall, and actually there's a lag. So it takes a while for that to travel, about 1 inch per hour. And again, if we wanted to be 8 hours later, that the heat from noontime starts to flow into the building, would make that wall 8 inches thick. Another way of thinking, another way in which this can be used. And here's a picture of a trom wall. This was the original house that was designed by Felix Trom. He's a Frenchman who developed this method of solar heating buildings. And here's his original building. So let's talk about a way this idea can be used in the summertime in a climate where the daily temperature difference between night and day is quite large. Let's say it's 100 degrees in the daytime at night, and maybe 50 degrees at night. 100 degrees in the daytime and 50 degrees at night. Here's how we could use that to moderate the temperature of a building. So let's say the building is made out of this. Building's made out of stone here. This part is stone, and it's 100 degrees. It's daytime, and it's 100 degrees outside and 70 degrees inside. So the heat flow is going to be in this direction. Heat flow is going to be in this direction because heat flows from warm to cold. And then it's going to start to flow, and it's going to take 1 inch per hour. It's going to flow in this direction during the daytime. But look what's going to happen at night. At night, the outside temperatures may be 40 degrees. Inside temperature is 70. So it's going to flow again from warm to cold. It's going to flow in this direction. Daytime in this direction, nighttime in this direction. So in the daytime it was flowing this way, but at night, at some point, it turns around and flows the other way. And so what can happen then is that heat cycles back and forth between this outer layer of the thermal mass of the building, of the concrete or stone of the building, and never actually comes in the building. This is why oftentimes stone buildings feel really cool in the summertime, even though they don't have much insulating, much R value, much insulating value. They cycle that heat in the outer layer of that wall. Now, if the situation were to stay like this for days, 40 degrees outside, 70 degrees inside, all the heat from the building would just flow outside, and so you wouldn't get any benefit. Or if it were to stay this way, very hot outside, cool, you want it cool inside, then the heat would just flow into the building like this, continue to flow into the building, and the building would get hot. It only works when there's that change in temperature. But in every climate, there's a season when you have that change in temperature, and you can use that to keep buildings comfortable. I think the last quality of heat that I want to talk about, heat energy, is phase changes. This is when a material changes from a solid to a liquid or from a liquid to a gas. For example, water is a solid ice, can change to a liquid, liquid water, and then it can change to a gas, steam. So a weird thing happens when phase changes happen, when something changes from a solid to a liquid or a liquid to a gas. Water, for example, as ice at 32 degrees to a liquid at 32 degrees, same temperature, it takes 143 BTUs to make that phase transition happen. It'll absorb 143 BTUs to melt ice. Then if we take liquid water at 32 degrees and we heat it to liquid water at 212, well, that's 1 BTU per pound per degree Fahrenheit. It's about 180 degrees Fahrenheit. It's going to take 180 BTUs per pound to change it from 32 to 212. Now look at this. To change it from 32 water ice to 32 water was 143 BTUs, same temperature. But to go from 32 degrees water to 212 water before it boils, it takes us 180 BTUs. Now this is even more strange. If we take that water at 212 degrees, water as liquid, to 212 degrees as a gas, we boil it and create steam, it's going to take 1,040 BTUs to change that from water at 212 to steam at 212. That's why steam burns you very quickly and very easily, because when that steam hits your hand, it condenses back to water and it gives back that 1,040 BTUs and tries to deliver that energy to your hand and burns your hand. So again, this is a kind of a strange property that happens when things change phase. And you can use this, for example, there are some waxes that melt at about 80 degrees. So you can have excess solar energy coming into a building, and you can have these maybe barrels of this wax, and as they start to, as the excess energy comes in, then they'll melt and they'll absorb energy, and they'll actually keep the building from getting too hot. And then at night, and they'll melt. So the wax was solid, it melts, it turns into a liquid, and then at night when the building starts to cool off, say it becomes 70 degrees and the barrel's at 80, the molten wax at 80, it'll condense back, it'll solidify back into solid wax, and it'll give back large quantities of heat. So this phase change is sometimes used for heat storage systems in buildings. So to summarize all this, heat is a special form of energy related to molecular motion, and it flows from warm to cold objects. Temperature, different than heat, it drops when heat flows out of an object and rises when heat flows into an object. In a similar way, during meditation, the mind naturally flows from greater activity to lesser activity to the field of least action, being. Just like heat flows from a highly active object to cooler objects in a spontaneous way. Just like in meditation, your mind flows in a spontaneous way from greater to lesser activity to being. We're just about done with this lesson, and I want to, and what we're going to do tomorrow is we're going to do a lot of calculation. We're going to practically apply these principles of energy and heat that we've explored kind of intellectually in this lecture. We're going to actually practically apply them and see how we can analyze renewable energy systems in terms of these quantities of energy and heat. So before we go to that, I want to just connect the parts of knowledge to the whole of knowledge with this unity chart. So the more common understanding is that energy comes in many forms that can be harnessed to do work for humans. But a deeper understanding that is energy is essential to the processes of change in the universe. Energy isn't just solar energy or gasoline or natural gas or wood or any other form of energy. It's fundamental to the processes of change in the universe. If we look at transcendental consciousness, it's unchanging. Nothing is created or destroyed. Nitya and aparashaya. Impulses within that transcendental field. The universe starts as an impulse within that transcendental field. And then in wholeness moving within itself, in unity consciousness, all change at the surface level of life is seen as fluctuations in my own consciousness. And again, I think you can see these analogies between these kind of mysterious properties of how energy transforms and changes with these properties of transformation and change within our own consciousness and within the unified field. Look forward to talking with you more about this in class tomorrow. This lesson is over for today.